Welcome back. In our previous videos, we studied infinite series and explored several important convergence tests. In this video, we begin a very important new topic called alternating series. Alternating series are series whose terms change sign repeatedly, positive, negative, and so on. In this lesson, we will learn exactly what alternating series are, how to determine whether they converge, and how to estimate their errors. Look at the famous example on the left side, the alternating harmonic series. Written out, it looks like this: 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus and so on. Alternating series are extremely important because these shifting signs can completely change how a series behaves. For example, we already know that the standard harmonic series diverges, but the moment we alternate the signs, the series converges. This happens because the alternating positive and negative terms cause a partial cancellation. And this cancellation is the driving force behind the convergence. If you look at the partial sums table on the right side, you can see this concept in action. Notice how the sums bounce back and forth. Our first partial sum, S1 is 1. Then S2 drops to 0.5. S3 goes back up to 0.8333 and so on. As highlighted at the bottom of the slide, these partial sums oscillate above and below a specific number, and they get closer and closer to a fixed value with every single term we add. This bouncing behavior strongly suggests convergence. But how do we prove this mathematically? For that, we need a formal test. To prove convergence rigorously, we use the alternating series test. It is also called the Leibniz Test. This test gives us three straightforward conditions under which an alternating series is guaranteed to converge. First, the term a sub n must be strictly positive. Remember, the alternating sign comes entirely from the power of -1. Second, the sequence of the term must be decreasing, meaning a sub n plus 1 is less than or equal to a sub n for all n. And third, the limit of a sub n as n approaches infinity must equal 0. If all three conditions are satisfied, then the alternating series converges. But let us pause for an important remark on the right side of the slide. Students often make the mistake of assuming that if the limit is 0, the series automatically converges. Be careful. The conditions that the terms go to 0 is necessary, but it is not sufficient by itself. We absolutely must also show that the terms are steadily decreasing. Keep that in mind as we look at some examples. Let us put the test to work with two examples. Example 1. We formally test the alternating harmonic series where a sub n equals 1 over n. Let us check our three conditions. First, a sub n is clearly greater than 0 for all n. Next, a sub n plus 1 is less than or equal to a sub n. So the sequence is steadily decreasing. And finally, the limit as n goes to infinity is exactly 0. All three check marks are satisfied. Therefore, by the alternating series tests, the series converges. Example 2. The summation of -1 to the power of n times n over n plus 1. Here, our a sub n is n over n plus 1. While the terms are positive, notice that what happened when we check the limit. The limit of n over n plus 1 as n approaches infinity is 1, which is not 0. Because this third condition fails, the sequence of terms does not vanish at infinity. Therefore, the test fails and the series diverges immediately by the divergence test. Our key takeaway here is very important. Alternating sign alone do not guarantee convergence. You must satisfy all three rules. One of the most beautiful and practical properties of alternating series is how easily we can estimate their errors. The errors estimation theorem states that if all alternating series converges by the alternating series test and we approximate its exact sum by stopping after n terms, then the absolute value of the remainder or error is strictly less than the magnitude of the very next term a sub n plus 1. In short, the error is bounded by the first neglected term. Let us look at the approximation example on the right side of the slide. Suppose we want to approximate the value of the alternating harmonic series using just the first four terms. Our fourth partial sum, S4, gives us approximately 0.5833. The very next term is magnitude is a sub 5, which is 1/5 or 0.2. According to our theorem, the absolute error of our approximation is guaranteed to be less than 0.2. This means the true exact value of the infinite series lies safely within the interval 0.5833 plus or minus 0.2. As you can see at the bottom, this property makes alternating series incredibly useful for numerical approximations. The more terms you calculate, the smaller your error bound becomes and the better your approximation gets. Now we continue with another very important topic in infinite series: absolute convergence and conditional convergence. First, let us look at the alternating harmonic series. This series converges, but if we remove the alternating signs, we get the harmonic series, and the harmonic series diverges. This is a very interesting result, but let us define absolute convergence. A series is absolutely convergent if the series made from the absolute value also converges. In other words, we ignore all positive and negative signs and check convergence again. If the absolute value series converges, then the original series converges absolutely. Now let us look at an example of absolute convergence. We want to determine whether this alternating series converges absolutely. To do this, we take the absolute value of every term. Then the series becomes 1 over n squared. This is a p-series with p equal to 2. And because p is greater than 1, the series converges. Therefore, the original alternating series converges absolutely. Now we state an important theorem. If a series converges absolutely, then the original series also converges. But the opposite is not always true. Some series converges, but they do not converge absolutely. These are called conditional convergent series. Let us define conditional convergence. A series is conditional convergent when the original series converges, but the absolute value series diverges. This means the convergence depends entirely on the alternating positive and negative signs. Without those signs, the series would diverge. The most famous example is the alternating harmonic series. The alternating harmonic series converges, but the harmonic series diverges. Therefore, the alternating harmonic series is conditionally convergent. Let us compare absolute convergence and conditional convergence. In absolute convergence, the absolute value series converges and the original series also converges. This is a stronger type of convergence. In conditional convergence, the original series converges, but the absolute value series diverges. This type of convergence depends strongly on cancellation between positive and negative terms. Today, we learned the meaning of alternating series, absolute convergence, the meaning of conditional convergence, and the difference between them. We also learned that absolute convergence always guarantees convergence, but conditional convergence depends on alternating signs. In the next video, we will study power series. Thank you for watching. If this video was helpful, please like the video and subscribe to the channel.